talking about strings at the end of last class, and we'll continue talking about them in this class. So there's a method called contains that returns true if a string contains a specified substring. So here I've got the string all caps CISC124. Right? I want to know, does that string contain the substring all caps CISC? Right? And so the way you call the method is you use the variable name, right, or a reference to a string. Right? So course name dot contains CISC, where CISC is a string. Right? And that returns a Boolean value, so it returns true or false. Does it contain the string all capital C, capital I, capital S, capital C? Right? And that will return true. Now, if you go and look at the documentation for the string class, right? So if you go looking for the method called contains, you'll find that there's exactly one. Right? So there's one method called contains, returns a Boolean, but it doesn't look like it takes in a string. Instead, it takes in something called a car sequence. So if you click on that and open that, and go and look at the car sequence documentation, right, you'll see it's something called an interface. It's not a class. It's something else. Right? So we're going to talk about interfaces a little bit later on, in probably a week or so. So I'll explain exactly what an interface is. For now, all you need to know that it is a type in Java. Right? So similar to a class in that it defines a type. But is it also a string? Well, a car sequence is not a string. It turns out a string is a car sequence. Right? And so there's a section here called all known implementing classes. And string is one of those classes. And so we say that the string implements this interface car sequence, which in Java is similar to saying a string is a car sequence. So when you go back here and look at this contains method, you can say, oh, yeah, I can pass in a string because a string is a car sequence. Right? And we're going to talk more about this in part 3 of the course, where we talk about something called inheritance. Right? So many weeks from now, you'll actually learn how to implement one of these inheritance hierarchies and do things like create a class that you can substitute for car sequence. Right? So for now, contains takes in a string. Notice what it doesn't take in. It doesn't take in a car. Right? So if you want to search for a character, right, does a string contain a character? The answer is, well, you can't do it with contains. Right? If you try to do this, your compiler will complain. It'll say, hey, there is no method called contains that takes in a car. Right? So instead, if you really want to use contains, what you have to do is you have to turn that C into a string. So either double quote it or concatenate it with another string. Right? So empty string plus the character C gives you back the string equal to C. Right? And so that will work. Right? So what should you do instead? If you want to search for a particular character, well, you look for a different method. Right? And it turns out there's several. One of them that you could use is called index of. Right? So index of does in fact take in well, it takes in an int, which is interesting, but it will accept the car, right? And it'll tell you the index of where that character appears in the string. It'll be negative if it doesn't appear in the string. Right? So the searching for a character methods are different than contains. Right? So index of returns the first location of a specified character in a string. Right? So if I want to know where is the first letter C, right, you pass in a car, right, and it will return 0 in this case, right, because the capital C starts at the very beginning of the string. Right? Where's the S? Well, it's at index 2 in the string. Right? Where's the 4? The first 4 is at index 6. Right? Where's the Z? Well, there is no Z in here. Right? So you get back -1. Right? So index of tells you the first location of a specified character in a string. Again, if you go look at the documentation for the string class, right, you see there's several index of methods. Right? There's one here. There's another one here. Right? So it looks the same as this one, except it also takes in a second index. Right? It takes in an index where the method will start searching from. Right? So if you ask s.index of, say, the A, starting from index, say, 3, it'll check whether or not there is an A at index 3, 4, 5, 6, 7, 8, et cetera, up to the end of the string. Right? So in other words, it'll ignore everything before the from index. There's also an index of string, which will give you the index of the first occurrence of a substring. Right? And similarly, there's an index of string and from index, which will tell you the index of the first occurrence of a substring str, starting at the from index. right? So there's a whole bunch of methods in the string class. You'll notice that the methods all have the same name, right? So they're all called index of. Their parameter lists are different. So this one takes in one int, right? This one takes in an int and an int. Oh, sorry. That one takes in a string, and that one takes in a string and an int, right? So they have the same name, but their parameter lists are different, which is legal in Java, right? So in Java, you are allowed to overload a method name. So that's the technical term for it, right? Two methods with the same name in the same class are said to be overloaded. They have to have different parameter lists, right? So if they have the same parameter list and the same name, the compiler will complain because it can't figure out which method you want, right? They both look the same to the compiler. All right, there's also a last index of, which instead of starting from the front of the string, starts at the back of the string, right? So what is the last index of the C? Well, it's not that one. That's the first one, right? The last C occurs there, which is at index 3. Where's the last occurrence of the S? Well, it's 2. The last occurrence of the 4 is 6, right? And there is no Z, so again, you get back -1, right? So there's also a last index of, and there's 4 versions of last index of as well. Okay, now in last class I told you if you were comparing two primitive values, use equals equals, right? Or not equals, right? Exclamation mark equals. If you have two reference types, right, like two strings, you almost always do not want to use equals equals, right? And this is confusing, especially since we taught you Python in your first course, because in Python you always use equals equals, almost always use equals equals, right? And now I'm telling you only use equals equals when you have primitive types. If you have strings, don't use equals equals because it's almost certainly not what you want to do. Right? If I want to test if two strings contain the same sequence of characters, right? Same number of characters, identical characters at each index, the method is called equals. Right? So if I want to check is that string the same as that equal to that string, it's CISC.equals_math. Right? And obviously that's false. Right? Case matters as well. Right? So lowercase CISC124 is not equal to all uppercase CISC124. Right? So don't forget this one. Right? Do not use equals equals to compare two strings for equality. Right? Unless you really know what you're doing. Hopefully by the end of the course you'll really know what you're doing. Right? But for now, if you encounter a situation where you want to test if two strings are the same, are equal, right? Use the equals method. Do not use equals equals. Okay? We've seen plus already, right? So the plus operator is string concatenation, right? Joins two strings together. So here I've got name 1, and here I've got name 2, right? Name 1 is James Bond 007, right? Name 2, I'm just going to join 3 separate strings together, right? So I'm going to take James with a space, and then Bond with a space, and then 007, join them all together, right? Are they equal? Yeah, they're equal, right? They're the same string when you join after the concatenation. Right? You can concatenate anything onto the end of a string, right? So if you have a string, you can add anything you want to the end of the string, right? And any type in Java, which is super convenient, right? So for example, here, I can take the string James Bond, right? And then I can concatenate the integer 0, the integer 0, and the integer 7. And that works just fine. Right? Now, you have to be careful when you do something like this. Okay? So when Java sees an expression like that, right, it says, well, I've got something plus something plus something plus something. Right? What is the precedence of all the operators in the statement? Right? Well, plus, 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 they all have the same precedence. Right? Because it's the same operator. Right? So the precedence is the same. So Java says, well, okay, I'm going to evaluate this expression from left to right. Right? So it's going to start with a string and try to concatenate a 0. Right? And that works just fine. Right? That produces a string. Right? So now it's a string plus a 0. So that produces a string. Right? And that's all a string plus the 7. That produces a string. Right? So everything's fine there. Right? Now remember, if it sees a bunch of plus operators in an expression and only plus operators, it's going to go left to right. Right? So if you try to do something like the following, right, it doesn't work. Right? Even though there's a concatenation with a string at the end here. Right? So if I start with the car H and the car A, right, and then add the string HA. Right? Java says, well, I've got plus plus, so I'm going to go left to right. So that's car plus a car, which you know gets evaluated as an int. Right? So whatever the integer value of h is and whatever the integer value of a is, right, those get summed together. Apparently they sum to 201. Right? That's now an int plus a string. Right? So Java says, oh, okay, I know how to do that. That's concatenation. So it takes the 201 and joins that with HA. Right? So it goes left to right. So you have to be very careful when you're doing string concatenation. Right? When you're doing string concatenation and not all of the types are strings, then you have to make sure at the front of the expression there's a string. Or you have to make sure you're doing things in the right order. Right? So for example, there's lots of ways to fix this. You could put parentheses around the A and the HA. Right? Parentheses have highest precedence in Java. So the A plus HA gets done first. That produces a string. Right? And then it sees the H plus some string, and so that's string concatenation as well. So you could solve it that way. Right? But the easiest way to solve this problem is always to put the empty string in the front. Right? So empty string plus H plus A plus HA will always work. Okay? You can get all sorts of weird results when you do this sort of thing. So if you read the string notebook, there's a few other examples of strange results when you're working with string concatenation. Right? You can avoid all the problems just by starting with the empty string. Okay, you can slice a string in Python, right? Because a string is just a sequence in Python. A string is not a. There's no such thing as a standard sequence in Java. So you can't use this square bracket with the colon notation to slice a string. Right? But there is a substring method that does the exact same thing. Right? So substring works exactly the same as the Python slice, except there's no negative indexes. Right? So if I start out with the string A, B, C, D, E, F, G, right? And if I call the substring method on S, then I get back the string, right? Made up of all the characters starting at index 1, going to the end of the string. So you get the B, C, D, E, F, G. Right? 3, 4 gives you all the characters starting at index 3, going up to but not including the 4. Right? Exactly the same as the Python slice. So that gives you back the D. Right? 5, 7 gives you back all the characters, the string made up of all the characters starting at index 5. So 1, 2, 3, 4, 5. And going up to but not including index 7. So that's FG in this case. Right? So the substring method is the analog of the Python slice. No negative indexing. If you use an invalid index, when you run your program, you'll get an error. Python has operator overloading. So you can redefine the meaning of less than, greater than, equal to, greater than, equal to, greater than, less than or equal to, etc. Java doesn't have that. So in Python, when you write s less than t with 2 strings, right, you get back true because a comes before z. Right? Is s greater than t? Well, you get back false because a comes before z. Right? Equals equals also works, right, with in Python. If you want the equivalent, if you want to do the similar thing in Java, you have to use this method called compare to. Okay? So the compare to method will compare 2 strings by lexicographical order. Lexicographical just means dictionary order. Right? So for 2 strings s and t, right, if you write s dot compare to t, right, then the answer that comes back is an integer value. Okay? It's negative 1. It's a negative value if s comes before t. Right? It's a positive value if s comes after t. Right? And it's the value 0 if they're equal. Right? If they're exactly equal. Right? If s follows t, yeah, okay, that's fine. Right? Right? So negative if s is less than t, positive if s is greater than t or comes after t, and 0 if they're equal strings. Right? So I've got aardvark and zebra. Right? If I write s dot compare to t, you get back some number, it's less than 0. Right? Because aardvark comes before zebra in the dictionary. Right? S compared to s is 0. Right? If you compare a string to itself, well, the strings are equal, so you get back 0. T compared to s, so is zebra, what is the order of zebra versus aardvark? Well, zebra comes after aardvark, so you get back a value that's greater than 0. Right? If you read the documentation for compare to, you can find out what the exact, what the value actually corresponds to. Right? Okay, if you want to replace characters in a string, characters or substrings in a string, you can use one of the many replace methods. Right? So again, go poke around in the documentation, look for replace, and you'll see that there's 2. Right? So replace old car with a new car. That replaces all occurrences of old car with new car. Right? Replace target with replacement replaces all occurrences of the substring target with the string replacement. They don't have to be the same length. Right? So the replacement string can be longer or shorter than the target string. Right? Okay, so I've got sparring with a purple porpoise. Right? If I replace all P's with a T, right, the string you end up with is starring with a turtle tortoise. Right? If you want to replace a substring, right, just give it strings. Right? So if I want to replace all occurrences of hi ho with oh no, right, then you just write s dot replace hi ho oh no, right, and you'll end up with oh no, it's off to work we go. Oh, cool. So there's lots of methods in the string class, right? Like if you scroll through this, so if I go back to the top, here we go, right? There's a bazillion of them, right? Not a bazillion. There's a lot, right? There's a lot of methods here, right? And so one of the problems that you have when you're working in any programming language is that you have to become familiar with the abilities of in this case, a class, right? The only way to do that is to actually go and read the documentation at some point, right? So at some point, you have to scan through the documentation and see what the string class is capable of, right? Because no one's going to produce a lecture where they go through every single method with an example, right? At some point, you have to get used to reading the documentation and figuring out what the methods do, right? A lot of them you won't be able to understand at this point, right? Because a lot of them have some funny names, funny syntax or funny names in them, right? This one's got a dot, dot, dot. You don't know what that means, right? This one's got this really bizarre question mark extends car sequence in less than or greater than. You don't know what that means. You'll know what it means at the end of the course. You don't know what it means now, right? So when you're reading this, you don't get intimidated by stuff you don't understand. You're not supposed to understand it yet, right? But you have to get used to reading documentation and at least being familiar with what the class can do. All right, any questions about strings? No? All right. The next lecture is lecture number 6. Okay, so one of the requirements of this course is that you learn something about what's called numerical computing. And basically what that means is we're going to try to teach you not exactly how numbers are represented on the computer, but sort of how numbers are represented on the computer. Right? Did they teach you about binary, like integer binary values in 121 or 101? Yes? Yeah? Super. Did they tell you about signed binary values? 2's complement, 1's complement? Did they tell you about that? I don't think they did. They probably wouldn't tell you about that. You probably only know the unsigned binary representation. So that's good, right? So you know how ints are, you know how non-negative ints are represented on a computer. They almost certainly didn't tell you how floating point values are represented on a computer, right? So that's what this lecture is about. In Java, you've got 2 floating point types, one called float, one called double, right? Double is the one you normally use, right? They approximate real numbers in Java, right? Why do they approximate them? Because, well, Java says you've only got a finite amount of memory to store a real number, right? If you try to write down so real numbers can have any number of digits, so you can't store an arbitrary real number in a finite amount of memory, right? So they're only approximations, right? Because they occupy a fixed finite amount of memory, you cannot represent every real number exactly. And the real numbers that you can represent aren't the ones that you think you could, right? So if I take 0.1 plus 0.1 plus 0.1 and add them together, right? All of you know it's 0.3, right? But if you ask Java, is x equal to 0.3, the answer is no, right? And you shouldn't believe me when I tell you this. You should just open up either an Eclipse notebook or fire up Eclipse. Sorry, open up a Jupyter notebook or fire up Eclipse or something like that and try it yourself, right? So here I've got a little main method. Can you read this at the back? Sorry, I shrunk the font to see if I could get rid of that editor problem, but it doesn't work. So I have to figure out what's going on. So I'm going to add those three numbers together. I'm going to create a variable called boo and set its value to x equals 0.3, and then I'm going to print the result, right? And the answer is false, right? 0.1 plus 0.1 plus 0.1 is not equal to 0.3. Right? This is bad if you're writing a banking application, right? So if you're writing some sort of financial application where you're dealing with some sort of decimal currency, all of a sudden you get weird stuff like this happening, right? And that's just because of the way that floating point numbers are represented on the computer. All right, so why does this happen? Where's my, no, that's not it, here. Okay. So why does this happen? Well, this doesn't explain why it happens, but maybe we can try to figure out what's going on. If I print out the actual value of x and 0.1 plus 0.1 plus 0.1, right? Now, if you actually try to do this, so let's try to do this the naive way, right? So why don't I do system.out, print line, let's do 0.1. Right, so I'm going to print out 0.1. Now let's run that. Right, and hey, you get 0.1. So you say, well, okay, well, number one, that's good, right? You would think I'd better get 0.1. Right, so let's try 0.1 plus 0.1. Right, and again, your intuition says you had better get 0.2. And you do? Fine. You say, well, what's going on? What happens if I do that? Right? Do I get 0.3? And the answer is yes. Oh, wait, no. The answer is no, I don't. Right? I get something else. It's very close to 0.3. It's not exactly equal to 0.3. Right? Notice there's a whole bunch of zeros followed by a 4. So something funny is going on. Now, what if I print out 0.3? What do I get for that? Right? Because maybe that's the problem. Maybe it's the 0.3 that's not being represented correctly. So I run that. And you say, oh, no, I do get 0.3, in fact. Right? But the sum of 0.1 plus 0.1, 0.1, 0.1 is not 0.3 for some reason. OK. So if you try to do this in a bit more of a sophisticated way, right? So here I'm going to make this method called allDigits. It's going to take in some double value. And I'm going to use this class called BigDecimal to print the digit, to print the value, sorry. Right? So BigDecimal is Java's arbitrary precision floating point number class. Right? Arbitrary precision means it can store an arbitrary number of digits if you ask it to. Right? Up to some certain limitations. Right? So when I pass it that double value to this method and then use this method to print out the value, you get something very different. Right? So here's that exact same class. So when I run this class, right, you start to see, oh, hey, there is something funny going on. So when I print out the value 0.1, right, it's not actually 0.1. It's 0.1 with a bunch of zeros and then a 5 and a bunch of other digits. Right? When I print out 0.2, or no, sorry, not when I print out 0.2. When I print out the sum 0.1 plus 0.1, right, I get 0.2, then a bunch of zeros and some digits. Right? Same with 0.1 plus 0.1 plus 0.1. Right? And same with 0.1 plus 0.1 plus 0.1 plus 0.1. But mysteriously, when I do that 5 times and print out the result, I get what appears to be the exact answer. I get 0.5. Right? Similarly, when I just print out the value 0.3 on its own, I don't get back 0.3. I get 0.299999 and a bunch of 9s, right? So it looks like the value 0.1 is not exactly representable. Right? The value 0.3 is not exactly representable. if you accept the fact that 0.1 is not exactly representable, then when I add them together, it makes sense that I'm not going to get 0.2, right? Because I've got 0.1 something plus 0.1 something. That's not 0.2, right? That's 0.2 something, right? And the same with 0.3, right? If I add 3.1s together, and if I add 4.1s together, it's the same thing. Oddly enough, if you add 5 of them together, you get back what appears to be an exact answer, right? So the conclusion at this point should be that, yes, in fact, something odd is going on. Right? Okay, so that output I just showed you is actually a little bit misleading. Okay? So if you are trying to write a program and you think you need the exact value of a double number, right? Or if you seem to think that you need lots and lots of significant digits, then writing something like that doesn't actually do what you want it to do. Okay? Okay, so a double has somewhere between 15 and 17 significant digits when expressed in base 10, right? So in our ordinary number system, right? But when I printed that out, there was way more than 15 or 17 significant digits, right? I think there's something like 64, right? Okay, so what's happening is that you're not getting the, so what's happening is that when I take the 0.1 and I convert it to the nearest double value, right? That value 0.1, that's in decimal. It gets converted to binary, right? So there's some sort of binary representation that now represents 0.1, right? So I'm now switching to base 2, right? When I ask big decimal to print the value, it converts the base 2 value back to base 10, right? And so that's why you end up with this big stream of digits, right? You're actually getting back the closest base 10 approximation of your base 2 value, which isn't the same as the original base 10 value, right? So if you ever find yourself wanting to type in 50 significant digits, it's a waste of time, right? When you type in a decimal literal, the computer can only represent up to 15 to 17 significant digits. All right, so what's going on? So what's going on is how these numbers are represented in Java. So in Java and in Python, most implementations of Python, right? The floating point numbers follow what's called the IEEE 754 floating point arithmetic standard. Right? One of the main architects of this standard won the Turing Award, in part for his work towards developing this standard. Right? So this turns out to be, I mean, pretty much every desktop computer follows this standard for floating point math. Now, all of the details, it's a standard, it's publicly readable. It goes on for pages and pages and pages and pages, right? So the details of this standard are way beyond the scope of this course, right? This would be the sort of thing you would study in graduate school if you went to a university where there was a program in numerical computing, right? So obviously we're not going to go to that sort of level. What you need to know in this course, though, is that whenever you have a floating point number on your computer, right, it has that or you can think of it as having this representation here, right? So every floating point number has the form plus or minus s times 2 to some exponent. S is an integer, e is an integer, right? So it's some integer times 2 to some integer exponent, right? So s is called the significand, e is called the exponent, right? They're both integer values. Okay, so why can you not? So why when I print out 0.1 is it not 0.1? It's 0.100000000 something, right? The answer is because if I try to write 0.1 as s times 2 to the e, where s and e are integer values, you can't do it, right? Okay, so proof is by contradiction, right? Assume that we can find an integer value s and an integer value e, such that s times 2 to the e is 0.1, right? And so you look at this for a second, you say, well, if s is an integer and e is an integer, there's no way it can be 0.1, right? Because that number there is less than 1. Well, e can be negative, right? So if e is negative, then it's 1 over 2 to some exponent, right? And so, oh yeah, in fact, it can be less than 1. Right? So we know right away that e must be negative, right? So keep that in mind. Okay, so how do I solve this? How do I find s and e? Right? Well, s times 2 to the e equals 0.1, right? I want to get rid of the decimal place, so I'm just going to multiply everything by 10. Right? So multiply both sides by 10. Right? 10 times s times 2 to the e is equal to 1. Right? Okay, now bring the e to the right-hand side of the expression. Right? So divide both sides by 2 to the e. Right? So 10 times s is equal to 1 over 2 to the e. Remember, I know that e is negative. Right? So that's the same thing as writing 10s equals 2 to the minus e. Right? Sorry, 1 over 2 to the e is same. 1 over 2 to the e is the same as 2 to the minus e. Right? Forget about the fact that e is negative right now. Right? Okay. Now e is negative. So I know that negative e is a positive value. So on the right-hand side, there have to be e2s, right? 2 times 2 times 2 times 2, e times, right? What's on the right-hand side? Well, 10 is 2 times 5, right, times s, right? Where s is some integer value, right? All the 2's on the right-hand side are prime, right? 5 is prime on the left-hand side. Right? So the prime factorization of the left-hand side cannot be equal to the prime factorization on the right-hand side. Therefore, there's no way the left-hand side can be equal to the right-hand side. Right? Therefore, you cannot represent 0.1 as a floating point exactly using that representation right there. Right? And so what do you end up with? You end up with the number that's closest, right? The binary number that's closest to 0.1. Right, which happens to be 0.1000000 something, right? All right. So float and double. So float takes up 32 bits. Double takes up 64 bits, right? So in other words, they behave both basically the same. It's just that float's the smaller version of double, right? They're binary values on your computer, right? The standard actually has a base 10 standard as well, but on your computer they're in binary. So trying to write these numbers down in binary is really awkward, right? First of all, I have to write out 32 or 64 digits. Second of all, you have to figure out what the heck is this sequence of zeros and ones equal to, right? Nobody wants that, right? So instead, I'm going to consider a much simpler representation, and I'm going to use base 10, right? But everything that I talk about here applies to what actually happens on your computer. So I'm going to use 4 digits, right? Only 4. So this is very easy to work with. Right? All of my floating point numbers are going to be a 3-digit number. So my significand has 3 digits. Right? My exponent has 1 digit, but I'm going to subtract 5 from it. Right? And these digits are between 0 and 9. Right? I have the restriction that that first digit is not allowed to be 0. Right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then some other digits after it. Right? So there's always 3 digits in the significand. The first one's not 0. That exponent is between 0 and 9, but I'm going to subtract 5. Why do I subtract 5? So that I can get negative exponents. Right? So my exponents can be in the range minus 5 to 4. Right? This is in fact how the actual numbers are represented on your computer. Right? There's some number of binary digits in the significand, some number of binary digits in the exponent, and you subtract an offset from the exponent to get negative exponents. Okay, so let's look at some examples. Right? So remember, all my examples, they have 3 digits in them, right? All my numbers. 3 digits in the front, in the significand, 1 digit in the exponent. Right? So what's the smallest the smallest number greater than 0 that I can represent? Right? Smallest number greater than 0. Well, that's 100, because that's the smallest significand that I can write down, right? Because the first number can't be 0, right? What's my smallest exponent? Well, it's minus 5, right? So the decimal value is 0.0100, right? So that's the smallest positive value that I can represent with this representation, right? What's the next smallest value that I can write down? Right? So the next smallest one, well, I have to make the significand go up by 1, right? So the significance 101 times 10 to the minus 5, right? So what's that? Well, that's 0.00101, right? So notice the difference between these two values is 1 times 10 to the minus 5, right? And so right away you see one of the implications of using this representation, right? What's one of the implications? I cannot write down a number between these two values, right? Any value between 0.01 and 0.101, I can't write that down, right? There's no way to do it with this representation, right? And so when you have a value that's between these two values, you have to choose which one are you going to use for the representation, right? Okay, what if I go up in order of magnitude, right? So suppose I go up to 100 times 10 to the minus 4, right? So that's equal to 0.01. Right? Now what's the next largest value? That's 101 times 10 to the minus 4, right? And so that's 0.101, right? Now notice something else weird happens, right? The difference between these two values is 0.0001. It's 10 times bigger than the difference here, right? 10 times bigger. So now the space between adjacent floating point numbers changes, right? So it's not just that I can't represent every floating point value, right? But the spacing between floating point values also changes as I go up in magnitude, right? Which is also weird, right? Here I could write down a difference, right? When my exponent is minus 5, I can write down two numbers that are within, so I can write down two numbers with this sort of resolution. Right? I go up by one order of magnitude, and then suddenly my resolution is 10 times worse, right? If you keep on going, right? So 100 times 10 to the 2, well, that's 10,000. What's the next largest value? Well, it's 10,100, right? The difference between floating point values is 100, right? I can't write down 10,001 with this representation, right? I can't write down 10,002, right? I can't write down 10,099, right? And so on and so on, right? When you get to 10 to the 4, right, now you can't write down, you can only write down every 10,000 numbers between 1 million? 1 million, right? 1 million and 1,010,000, right? So finite number of floating point values, spacing between them changes, right? The spacing changes with the exponent. Oops, sorry. All right, so this funny thing over here, this difference that's happening, right? So the distance between adjacent floating point values changes depending on the value of the exponent, right? That distance is called the ULP, the ULP, right? So the ULP stands for unit in the last place, right? Why is it called the unit in the last place? Because it's the unit in the last place of the number, right? It's the unit in that third digit there, raised to that exponent. So that distance is called an ULP, and it's useful for measuring error of floating point values, right? The math class actually has a method called ULP, which will tell you how big is an ULP for that floating point value, right? In other words, it'll tell you what is the distance to the next floating point value. What is the distance from D of the next floating point value? What is the distance from F of the next floating point value? Okay, any questions so far? All right, so I have to make a decision on whether or not I want to continue, because we're going to start to do a bunch of math. It's not hard math, don't worry, it's not hard. All right, let's do a little bit. Okay, so when you're talking about floating point numbers, you know right away that there's probably going to be some sort of error associated with your when you do some computation with floating point values, right? Because number one, when I type in a decimal value, I probably can't convert it exactly to the computer's floating point representation, right? So in other words, it probably doesn't have an exact base 2 representation. So right away there's some error, right? Just in writing down the number, right? Now if I take two values and do some arithmetic with it, and those two values have error in them, then it's not surprising if the answer also has some error in it, right? So we need a way to talk about how much error is there, right? So one quantity is called the absolute error, right? So the absolute error, x hat, that's the true value of whatever it is you're trying to calculate, right? X is the value of your calculated value, right? What's the error? Well, you just subtract them and take the absolute value, right? So that's called the absolute error. So when you convert some decimal value, right, that fits in the range of a floating point type, right? When the computer stores that value, the absolute error is within 1/2 an ULP, right? Does that make sense to everybody? Can you understand why that must be true? Right. Just go back to the table, right? So I write down some value, say between 10,000 and 10,100, right? Pick any value you want, 10,001, right? So if I pick the closest floating point number to 10,001, that's 10,000, right? What's the error? It's 1, right? It's 1 in 100, right? 1 in 100. So, sorry, an ULP is 100, right? My error is 1, right? If I pick a value 10,099, closest floating point value is 10,100. What's the error? It's 1, right? The worst error that I get is if I pick a value that's exactly halfway in between, right? So if I pick 10,050, what's the closest number? Well, it's either 10,000 or 10,100, right? What's the difference? It's 50, right? What is 50 relative to 100? Well, it's 1/2, right? So it's always within 1/2 an ULP, right? So whenever you write down some floating point value, you're guaranteed to be able to represent that value to within 1/2 an ULP of that value. Okay, let's stop there because, yeah, let's stop there. If I start this now, I won't get through enough of the material, and then you'll forget it by Monday. So stop there, and we'll pick things up on Monday. Remember, you have an assignment due on Monday. If you have any questions about your assignment on the weekend, just fire me an email, and I'll try to get around to looking at them sometime during the weekend.